everyone. Thanks for joining. I think we've got a number of people shuffling in. So while everybody is getting settled, let's go over some of our housekeeping for today's session. You can expect about 40 minutes of content where Kevin from Datadog and Nick from NoBS are going to take us through some of the setup and then give us a live demo. At the end, we're going to wrap up with Q&A. We'll go ahead and drop any questions that you have throughout the session in the Q&A at the bottom of your screen. And we'll try to get to as many as we can. If we can't get to them, don't worry, we're going to follow up with you after the fact. Today's session is being recorded. If you have any questions about whether you're going to get the slideware or any of that, yes, you'll get a link to the deck and the recording. So with that, I'd like to hand things over to Kevin and Nick for some intros and all the good stuff.
Awesome. Thanks, Jess. Welcome, everyone. Quick intro for myself. My name is Kevin Goldschman. I am a partner solutions architect here at Datadog. I've been with Datadog for just over 3 years now, working directly with NoBS as one of my partners for a couple months now. Today at the end, I'll be giving the demo. My role here at Datadog is to kind of help with our partners, anything technical related. So technical enablement, demos, questions, etc. So, if you have any questions regarding the demo afterwards, feel free to ask them and I'll be able to answer to the best of my ability. So I'll pass it over to Nick.
Thanks, Kevin. Thanks for joining today, everyone. My name is Nick Picellio. I'm the principal engineer over here at NoBS Tech. NoBS is a 100% dedicated to Datadog professional services and consultation group. Myself, I've worn pretty much every hat in this industry, but for the last probably 7 or 8 years, I've been focusing on observability primarily, but I've been the site reliability engineer, the database administrator, the application developer, and everything in between. And what makes me particularly qualified to give this presentation today is that I have also been one of the leading causes at a place or two, and my personal wallet included, for cloud cost directly related to Kubernetes. And I have been yelled at for that before, and I am here to help you not get yelled at by the guy that holds the wallet. So without further ado, we can get back into the Kubernetes side of things. So just a little bit of a history lesson here. So it's been about 10 years or so since Kubernetes was officially released to the public by Google, of course, therefore meaning that GKE was the kind of first available iteration of it at first. Over time, services like EKS and AKS followed up, allowing you to create a cluster through a UI. And then tools like Kops, Helm, Minikube, Istio, and plenty of others followed in the next few years, allowing for a rapid deployment of Kubernetes, kind of button click based deployment. And it's very, very easy to get things stood up these days. Following that, Pokemon Go was a huge case study around the first few years of release. And if you guys remember that, it was a huge phenomenon where everyone was out walking around in public, catching Pokemon on their phones and everything. But what really was important about this for this context is that this was all running in Kubernetes. And this was one of the first kind of major case studies that revealed that you could, in fact, run Kubernetes at a huge scale, supporting millions of users at a time. So it started pushing people towards seeing that, it was something that was production ready and ready to go. And these days, Kubernetes is everywhere now. So there's edge installations of K3s and satellites. There's IoT systems in breweries, management of autonomous robots in hospitals. So the adoption has truly become widespread. Hey, Kevin, what was your first experience with Kubernetes and how was it to manage?
Yeah, it's a good question. Semi-embarrassing as an engineer, but I'll save you the details. But I think my first experience was probably with Minikube. So, kind of entry level into Kubernetes. And I quickly realized I was in over my head with, all of the different settings that you can be adjusted, resources, etc. So, I got about 10% in, felt good. And then after that, realized that it can be a little bit more complex than anticipated.
Certainly can. So given that it's so easy to stand this up and get it running, and whether you get it to 10% or 100%, there's got to be a catch, right? And Kevin just kind of hinted at this just a moment ago. One of the catches is that it's very easy to get caught up in complexity, especially when you start looking around at all the various add-ons and management tools that you can add. We've got things like, let me take a deep breath here. Istio, Linkerd, MetalLB, Nginx Ingress controller, AWS load balancer controller, cert manager, external DNS, gatekeeper, Valera, Argo CD, Flux, Kita, cluster autoscale, Cilium, Calico, Longhorn, Rook, and Ceph. And how do you know which of these to use and why or why not? That was really only just scratching the surface, but that's about as long as I can kind of hold my breath for. So we have that kind of initial hurdle of complexity and understanding what you really need to run your cluster in the first place. But then you have the additional problem that, you know, it can already be hard enough to manage a suite of VMs running applications, a pattern that people have been using for years and years and years. And now we have to learn distributed systems and containerization and keep the platform performant and stable. It's a pretty big task. So in addition to all of that, kind of already hinted at the tooling here, but you'll definitely need some sort of plumbing to have a good experience, right? So CI/CD platforms like Argo allow you to roll out your applications. DNS controllers can automatically create records on automatically created load balancers, and so on and so forth. And then, of course, you need the team that has the experience to run this in production. So while it's becoming easier to find over time, it's still a skill set that can be independent from other aspects of engineering. Now, this kind of varying levels of complexity here, you might have the right people and everything. There is one common catch. The biggest catch is that compute resources are not free. So complexity and skill sets and everything aside, we all have to maintain cost. Whether you're on-prem, whether you're in the cloud, there is always a cost to running your compute resources. Runaway applications with poor resource allocation and scaling practices can skyrocket those costs very, very easily, and you're not likely to find out about this until the cloud bill comes. Hey, Kevin, the first time you installed a Helm chart, did you care about the resources block?
Yeah, another good question. At the time I didn't, and I think we share a similar story, and maybe other people on the call do as well. But you know, starting with a free trial on GCP, you know, expecting nothing to come out of my bank account, you know, not worrying about those resources. You know, turns out 4 months down the road, get a charge for something that I, you know, didn't really care about in the beginning. So you know, came around to kind of bite me in the butt there.
And that is a perfect segue into how do we maintain performance and cost efficiency. So the two most common issues that lead to high cost are poor resource allocation and poor scaling practices. And these two concepts directly affect one another. When it's done well, you have a nice and stable and cost-efficient cluster. And when it's done poorly, hide your wallets because the boss is coming for them. So let's talk about these two concepts a bit more in depth and how they work for and against each other. So to start this discussion, we really need to understand how resource allocation works in Kubernetes. This is done through requests and limits of CPU, memory, and GPU when that's applicable to your use case. So requests are going to provide the minimum amount of resources a pod is given at startup. Just as a kind of a side note, some of the newer versions of Kubernetes allow for resource definitions at the container level or the pod level, given that you can run multiple containers in a pod. Previously, it was just the pod. It's just a little bit of a side note, but it is a cool feature that's out these days. Limits is the hard cap on resources that can be used by a given pod. When too much CPU is used, the CPU resources are throttled, which results in significant performance degradations, bearing in mind that Kubernetes is effectively a resource scheduler. And if you define one CPU, that doesn't mean you get one whole CPU. It's still a shared resource that needs to be scheduled. So if you're overusing it, it will become throttled to prevent additional damage from the rest of the cluster. If memory goes over the limit, the pod is out of memory or killed and restarted without any warning, which could, of course, result in downtime or performance issues if that happens. And this happens without warning, so we got to be careful. There's some very, very common mistakes when allocating resources. So if you don't set requests or limits, containers can use whatever they want and whatever they claim until the resources on the node run out, which of course causes other problems. When requests are set too high, Kubernetes spreads out the workload because it thinks the apps need more requests, more resources than they actually do. When resources are too low, this could lead to the aforementioned performance issues and, more importantly, incorrect autoscaling. And something to keep in mind here is that Kubernetes doesn't know your app. It doesn't know how much CPU you actually need to serve traffic appropriately. It is just doing what you tell it to do and working with what you give it. It's really not uncommon to see new users to Kubernetes trying to provision the amount of CPU and RAM that they're used to on static virtual machines or physical machines that otherwise didn't scale, and try to apply the same kind of vertical scaling techniques to their Kubernetes pods. I once worked for a place that was migrating from on-prem virtual machines to Kubernetes. And you should have seen the resource requests that were coming in on PRs for new deployments. They were, in fact, looking for things like 8 CPUs and 16 gigs of memory and things that people were used to when they were running 1 or 2 copies of their applications across various machines. Without the kind of full understanding that we are now running multiple replicas of those applications and they don't need all the horsepower that was assigned to them originally, if they even needed that in the first place. So if we had accepted those, we would have been very, very deeply underwater cost-wise extremely quickly. So we'll come back to resource allocation in just a little bit, but for now, we should also discuss autoscaling. It can be your best friend or your absolute worst nightmare. There are definitely many flavors of autoscalers out these days, but the most common are what you see on the screen right now. So the horizontal pod autoscaler, or HPA, scales pods based on CPU, memory, or other custom metrics as you define it. The vertical pod autoscaler, or VPA, can adjust requests or limits of the pod dynamically based on usage over time. And then the cluster autoscaler adds or removes nodes based on pending pods that have scaled up because of something like the horizontal pod autoscaler and that need a home to live in. So when autoscaling works correctly, it's wonderful. The HPA will see CPU usage rising and tries to create enough replicas to keep CPU utilization at the desired level. So then it scales them out. The cluster autoscaler then sees that these new replicas need to be scheduled and adds nodes to the cluster. The new nodes come online, the pods are scheduled, the traffic is handled, and the users or customers are happy and never have a clue what's going on behind the scenes. And of course, your on-call person is happy too, because they didn't have to wake up to alarms in the middle of the night to try and go fix these issues. Having been holding that phone for many years in the past, when autoscaling goes right, it makes me very, very happy, very personally. But it can also go very, very wrong. So we'll give a quick example here. Let's say you have a pod that requests 2 CPUs, but only uses half of 1 CPU the vast majority of the time. You're also running 4 replicas of that pod. Let's say that your cluster nodes have 8 CPUs. And just a real quick note before the rest of the example here, bear in mind here that 8 CPUs on a given node doesn't necessarily mean that all 8 of those are fully allocatable. We do still need some resource overhead required for the underlying operating system in the kubelet and some other necessary items. So for the sake of this example, we'll say it's a full 8, but always bear in mind it's going to be a little bit less than that. But anyway, to accommodate these pods with high requests compared to usage, the cluster autoscaler adds a node for only 1 pod. You now have underutilized compute, which is going to lead to higher cost. While 1 extra node might not break the bank, this is really only a basic example. Kevin, have you ever seen an autoscaler go rogue?
Yeah, a few times. Typically, when I've seen it, the autoscaler kind of will see a random spike here or there. Not necessarily a consistent spike, but it'll kind of begin its scaling, and then down the road we see those extra costs that might not necessarily have been needed at the end of the day.
So, given what the example that we just gave, how bad do you think this particular situation itself is?
I would say it could be pretty bad, right? And it depends on your exact environment, but most likely going to lead to unnecessary costs there.
Should we talk about when it goes really, really wrong?
Yes.
Okay. So here's where it goes really, really wrong. What you're going to see on your screen right now on the left side are 2 definitions here. We just have a quick resources block for a pod, and then an autoscaling configuration for that pod as well. So we have a pod that requests 100 millicores of a CPU. So really, 1/10 of a CPU with a limit of 2 full CPUs, bearing in mind that these are incremented in units of 1,000. We tell the autoscaler to target 50% utilization of the CPU resource. Now, here's the trick. This utilization is based on the requested resources. So basically, the HPA here is going to think that it needs to scale pods when that pod is using 50 millicores of CPU with a 50% utilization of 100 millicores. If your app regularly operates around 500 millicores of CPU usage, for example, the HPA will never be able to get the load down to the desired utilization. Now, if we take a look at the max replicas here, we'll see that the max replica is set to scale out to up to 100 replicas. So then the cluster autoscaler kicks in. And then that costs a lot of money for no real benefit. The boss is mad because of money. So now we'll come back to fixing this in just a few more important points, but bear in mind, we'll get more to this later, but you do need to properly right size your request so that this situation doesn't happen. All right, so back to resource allocation for just a second here. We also need to understand what a quality of service in Kubernetes is. So QoS is used to prioritize workloads when the cluster is under contention. A little bit more on that in just a second. There are 3 types of QoS classes. Guaranteed QoS is when a CPU and memory requests and limits are both set and they are equal to one another. So say you request 1 CPU and have a limit of 1 CPU, 1 gig of memory request, and 1 gig of memory limit. That is a guaranteed resource request or quality of service. Burstable means that requests and limits are both set, but are different values. So like the previous example, something like we set the request at 500 millicores and limited at 1. This has a mid-level priority under cluster contention. Best effort means that no requests or limits are set at all. This is the lowest priority and the first to go under contention. So why does this matter? In times of high utilization in the cluster, Kubernetes will start to evict pods to maintain stability under that resource contention. Eviction winds up being largely based on quality of service. When certain thresholds in the cluster are met, pods are then evicted to maintain resources in the cluster to certain levels. Now, to be clear, there are 2 methods of how essentially eviction occurs within Kubernetes. There is eviction and there is preemption. Preemption occurs when a pod needs to be scheduled, but a node doesn't have enough resources on it. So it will remove a pod with a lower priority to make room for that pending pod. But that is not related to quality of service. Only eviction relates to quality of service. So QoS and requests directly influence how a pod is scheduled, and efficient request settings allow for more optimal pod placement and an effective cluster resource utilization pattern. Additionally, a nice benefit of using guaranteed quality of service means that pods can take advantage of a setting in Kubernetes, allowing for static CPU management policies. So I mentioned a little bit earlier that Kubernetes is effectively a resource scheduler, and these resources are shared even if you say 1 CPU. That same CPU might be doing work for a lot of different applications. If you set a CPU management policy, that means that those CPUs are actually solely dedicated to that pod, which can be an absolute lifesaver for CPU-intensive workloads that can't really handle context switching. All right, so let's start tying all this together. Given what we know now, how do we set these sorts of things for performance and cost? When it comes to performance, we desperately need to avoid CPU throttling, which means setting requests and limits for individual apps appropriately. One size does not fit all. You do have to tune these to be appropriate to your workload, your traffic, and what your applications are actually doing, and even what language they're written in based on overhead. Proper memory settings can help to avoid killed pods or out-of-memory killed pods, making them unavailable, so we have better insurance that your applications stay up and available. We absolutely need to set proper resource requests to help out the autoscaler and have it make good decisions. Bad request settings means inaccurate scaling, which likely means higher costs or potentially poor performance due to cluster saturation. So utilizing what we just learned about QoS, sensitive apps should have guaranteed settings, less sensitive can be burstable, and we should always work on removing best effort where possible. Something else to consider here, and this is a little bit of a new concept here, but consider separating out your node pools for different workload types. A lot of times I see clusters where they just have a pool of worker nodes and everything gets scheduled there. You may want to consider something like a high CPU pool for CPU intensive apps where there's more CPU or a better performing CPU allocated to those nodes, or a higher memory pool for memory intensive applications. Now, the trick here is that you definitely need to make sure that you're using node selectors or affinity settings on your deployments to make sure that those pods are getting scheduled in the right place. Something else you may want to consider doing as well is separating out a system-based pool. So running things like if you're running any other internal tools to the cluster or additional controllers or everything, if those live on their own set of nodes, they can still work with the rest of the cluster, of course, but they are not potentially interfering with any other applications, and your applications are not potentially knocking the system stuff out of the cluster as well. So speaking of affinity and selectors, definitely pay attention to where pods with various quality of service settings live. Best effort pods can still cause contention on busy clusters. So you may want to also consider kind of not necessarily quarantining those, but being sure that you understand where they are placed. But you're not going to use best effort settings anyway, right? All right. Another thing to mention, and I may have already mentioned on the slide, but make sure that you're continually reviewing your application's resource utilization needs. Tuning is not and never will be a one-time exercise, as things change over time as applications grow in size, traffic, features, third-party dependencies, so on and so forth. So this is something that you do regularly need to pay attention to. So let's talk a little bit about resource settings for cost. There's a fun little concept to introduce here called bin packing. This is where we try to fit as many boxes as possible into a bin, kind of like a game of Tetris, except with containers. This is effectively where we're trying to maximize compute resource utilization for lower cost and highest efficiency. So in the example on the left-hand side of the screen, say that we have a compute node with 2 CPUs. If we have 2 pods that request 900 millicores, that is 1.8 out of 2 cores. If we want more replicas, we need more nodes, inherently leading to higher cost. But if we understand our standard resource utilization of this application, what can we do now? We can actually tune this to be a bit more appropriate. Let's say that maybe this is more like 500 millicores. Now this same node can fit 4 replicas. And of course, don't forget that this is all a little bit theoretical. Allocatable is not necessarily the specific amount of CPU on the node. So this is all well and good in theory, right? We talked a lot about conceptually, and I showed you a few examples, and it seems pretty straightforward, but we haven't actually looked at any real data. So, like, help me. How do we actually observe and understand all of this? So the beautiful thing is that Datadog offers a number of features that we can utilize with ease to help us understand this and take action on it as well. So we have the Kubernetes Explorer, where we can see our resource settings and utilization in real time. We also have the Kubernetes Cost Explorer, which allows us to see the cost of our clusters down to the pod level for dollars and cents. And additionally, we have the Kubernetes Autoscaler that allows you to change pod resources on the fly directly through Datadog and helping you understand what those cost comparisons would be if you made those changes. And that's all based on data that's collected through Datadog to make those intelligent decisions. So now at this point in time, Kevin's going to take us on a walk through all of this.
Awesome. Thanks, Nick. Go ahead, share my screen here. Awesome. Cool. So, Nick presented a lot of super useful data, but if you're like me, you can only handle one thing at a time. It can be overwhelming, right? Kubernetes can be overwhelming. So Datadog comes into this where we are able to take all this information and aggregate it and put it in front of you in a way that's much easier to digest. So, if anyone is not familiar, just a very brief intro into what Datadog is. We're that cloud SaaS platform that is used for cloud infrastructure monitoring and security. So, essentially, like I said, taking everything from your infrastructure, all the metrics that your applications provide, bringing it into one single pane of glass so that everyone can kind of be on the same page, viewing the same information. So for this demo, kind of piggybacking off of what Nick said, we'll cover how we present that Kubernetes information for you, and then what you can kind of do with that information, and then lastly cover how we can see those costs, maybe view our unused idle cost in what we can do to save money there. So to kick it off here, this is going to be our container host map view. So this is the bird's eye view into all containers reporting from your environment. The top right here, we can see that currently we are looking at the total CPU percentage. And at the bottom right here, you can see the color legend. So green being good, red being bad. Nick, if you were kind of, brought in as the engineer here, what would be your first thought, first thing you would want to do if you're kind of looking into, maybe some issues with your Kubernetes environment?
Yeah, so right now, as we take a look at this, this is, by default in this view, it's always going to be set by availability zone. And availability zones can have, clusters can run across multiple availability zones. So right now, all we see is a view of pods at that level, which doesn't really tell me exactly where they're running or what they are. So the first thing that I would do to get a better view of this is, instead of using availability zone as the grouping facet, I would probably choose something like cluster name and maybe deployment or node type or something that's a bit more closer to the machines and the cluster itself. And it looks like Kevin's putting that in right now so we can get a closer view of this.
Yep.
And there's other facets as well. So we can separate things by namespace or deployment or stateful set or any of the facets that Datadog provides on the metrics here. So this is kind of a better view to understand what's exactly running where. And, you know, the colors have changed as a result of the grouping because these are all relative.
Perfect. Thanks, Nick. So yeah, like you said, we changed our groupings here. So now we're grouped by cluster name and node pool. So you can adjust those tags as necessary to kind of view this environment how you see fit. So now that we're kind of looking at this in a little bit different view, mostly is showing up green, a little bit red here and there as these clusters. But we can see specifically that this cluster is going to be a little bit more red than all the others. So this would kind of give indication into something you may want to look into as this cluster may be running hot on that CPU. So if I were to do that, I would come around, I would be able to explore these. You could hover over them, their names will pop up, and then say we found one that we wanted to look into. We'd go ahead, click it. That's going to zoom in our view here. And now we're looking directly at this container here. So a few pieces of info. We get that container name. We have the host name, all the tags coming from this container. So everything that you may need to kind of, dive a little bit deeper into. These can be set manually. They can also be set automatically. So a good combination there. And then you get that quick glance into some metrics on the right side here. So we're looking at that total CPU percentage and then that RSS memory as well. So now that we've found this, we can click a little bit deeper. I will click that container name. We're going to dive in deeper. This container might have come up and then went offline. So that's why we're seeing no matching results here. But you can see as I click that container, it automatically populates our query to contain that container ID. I'm not going to be able to remember that, that ID right there. So it's easy, we do it automatically. You don't have to kind of copy paste those container IDs right there. So bring up some more useful information here. I'll get rid of our search query. And now we're taking a look at every single container reporting to our Datadog org here. So this is kind of going to be that overview for containers. Up top, again, we have some metrics, some time series metrics here. Right now, we're looking at that total CPU percentage, RSS memory. These can be adjusted as needed. So if you're interested in other things, you can change them. You'll be able to see, each container kind of broken out here. So, right off the bat, we can see that this specific container is going to have that higher system CPU than all the other ones. Over here, we're looking at IO reads. You can see some spikes here and there. But overall, you can, use these two graphs to kind of get that quick glance into the metrics behind those containers. Below, we have that container list. We have the container name, we have the current status, the image, and then on the right here, we're going to have some utilization metrics to kind of give you that quick glance again. So CPU, RSS memory, some bytes. You can see when it was started. So these, top two containers here have been going for 2 months. Down here, you can see that we have some started 2 hours ago. So some general metrics here. On the left, kind of like Nick was mentioning, we have all those facets that you can use to filter down. So if you're looking for specific cluster, deployment, service, whatever you may be looking for, we make it easy to kind of, select that option here. And now we're looking at all the containers related to that auth.net service. So I'm going to clear this. Let's go ahead, look into, let's say, the product recommendation service. So what I'm going to do here, let's click one that's still live. So now we are looking at that more specific container page, right? So this is going to be all the information needed to look into that container. So on the left here, we can start with that resource metrics. Again, these are all going to be drop downs that you can use to change the various metrics that you're looking at. So if you're looking into specific metrics, change those right there. Get that easy, quick glance into how that actual container is behaving. And then up here, we're going to have some options for viewing related resources to this container. So currently, we're looking at related processes. So you can actually see the processes that are running currently on this container, right? This is going to save you a bunch of time of having to manually, go into your Kubernetes environment, look at this stuff manually. I never remember the commands to do that. So instead, you can just pop into Datadog and see that right in front of you right here. You can select this drop down and you'll be able to see that, we have that list of related resources. So we have clusters, nodes, deployments, anything you want to see that's related to this container, you can do so right there. Awesome. So what I'll do here is let's go ahead, click pods. Now we can see the pods related to this container. Some quick utilization metrics right here. Let's say we want to look into this pod specifically. We can click that directly from here. It's going to open up a new page. And now we're looking into the pod. So similar view, a little bit more items here on these tabs, but same idea here. So at the top, we have all of the necessary information that you need to understand kind of where this pod lives, all the resources related to it. Again, we have that age here. We have restarts if you're looking into, how many times that pod has restarted. And then below we have some important information. So this first tab that we're on now is going to show you the YAML file that's responsible for essentially building this pod, right? So Nick, to bring you in here, if you were, again, the engineer brought up to kind of troubleshoot a pod, what would you be looking for maybe in this YAML to kind of understand maybe some resources or just get some more useful information?
Oh yeah, so I use this all the time because in a huge cluster, it can be kind of difficult to make sure that you're in the right namespace or that you're looking at the right pod or have the metrics pulled up right beside it. So by the time you've already gotten to this point, you don't have to worry about inspecting the deployment or running, like, do I run describe or do I run get? You have the full manifest right here. So you have the ability to go through and see exactly which settings are on here. So even in items like environment variables, it won't show you the values of those. Those are still secret, but you could see what's assigned, so you can look for any misconfiguration. You've got the entire definition of this right in front of you. And then one of the nice parts about this pod view is that there is also an option up there called troubleshooter. So for this one, it's probably not going to show much, but if a pod is in not a great state and it continues restarting, it'll actually pull this information out for you to show you, like, if what pod phase it's in, is there an issue with an init container, is it an image pullback off? So really kind of quick hit items right within Datadog to be able to inspect your individual pods or deployments without having to go through the cluster and everything.
Awesome, thank you. One more thing I want to mention on this YAML file, if we scroll down here at the bottom, so Nick mentioned a few times kind of, the resources related to your environment here. So you can actually see that directly inside of this YAML file. Again, saving you that time of having to go into your cluster, remember those Kubernetes commands, looking for the YAML files, whatnot. You can come to Datadog, pick out that pod you're interested in, see that information right there. A few more important things to kind of go through on this tab. This feature is one of my favorites. I'm a visual person, so I like to see the visual layout. This related resources tab is going to show everything that we kind of saw in that dropdown. It's going to put it on this map here. So right here, we can see the pod that we're scoped to. And then below and above, we can see all of those dependencies. All the way to the top, we can see the cluster where this pod is located. Below, we can see the container. And then, we can actually see those processes running inside that container that I showed before. So super useful for those visual people to be able to come in here, take that quick glance, get that bird's eye view into, this entire cluster and all the resources that are located inside of it. Lastly, cover these few things. So One thing Datadog is really good at and kind of sets us apart is that correlation across all resources. So you can see we have the logs, APM, metrics, network events, monitors. All of these things are going to be correlated across your Datadog org. So right now we're on that logs tab. What we're seeing here are all the logs coming directly from this pod. So you don't actually have to log into the pod and run the command to view those logs inside. You can actually just come here to Datadog, view those logs right here. Same with APM. If we click over here, we can actually see all of the traces that are coming from this specific pod itself. So again, saving you that time gives you more time back to kind of look into that troubleshooting rather than just getting to where you need to be to start that troubleshooting. And this goes across, metrics, network. We can see all the network information related to the pod here and the events. And then if you happen to set up any monitors for the pods, you will be able to see those here. Also, we list some suggested kind of starting points for monitors here. If you are, new to Datadog and don't necessarily know what you need to monitor, we offer some suggestions to get you started right out of the box there. So now that we kind of have a general overview of that Kubernetes Explorer, let's zoom back out slightly. We'll go here to that Kubernetes overview. So like I said, we're kind of zooming out here. Up top, you get that general sense of what your Kubernetes environment is actually looking like. So put some numbers right here in front of you, get that quick glance, 19 clusters, 229 nodes. Again, saving that time of having to kind of track down manually going to your Kubernetes environment and, kind of writing on a notebook. Instead you can come here, just check this, takes 30 seconds. Below is what we'll get into next. So we understand that Datadog offers the ability to kind of get that information into your Kubernetes environment, see the utilization, see the YAML files that are responsible for building, your resources. Nick talked a lot about cost and the possibility that Kubernetes can lead to unnecessary costs if you're not careful when you're kind of building your resources. So what we do here at Datadog is put that information in front of you to kind of show you where that money can be saved. So these two tabs right here, the one on the left is going to show you the cost of unused resources. So kind of that cost that is, out into the wind, right? You're spending money on things you don't necessarily need. On the right, we have deployments by autoscaling service or status, sorry. So we take your entire environment, we show you where autoscaling has been enabled, where it's available, and then where it's unconfigured. So, quick look at this. I can see that we have 0.68% autoscaling enabled across our environment. I would want to bump that up, right? We want to save money. That autoscaling is ideally there to kind of help us with that. Dive a little bit deeper. So you understand from this that we have a total cost of $2.5 million, and then 1.7 million of that is going to be that estimated idle cost. So money that you're spending for idle resources, right? So we have that idle cluster cost here, and then we have that idle workload cost. So say that I have, someone on my team, my manager has tasked me to kind of optimize our spending. We're spending a lot of money. It seems like we have a lot of money going into something that we don't necessarily need. So what I would do here, I'd click this optimize your clusters. This is going to bring us to that auto scaling. So now this is showing a list of all of our clusters here. We get some utilization metrics here on the right. We can see our CPU idle, we see the unused memory, and we can see that cost and then that idle cost per month here, right? So if we look down, this is going to be our big number here. So this specific cluster is costing us just over $2 million per month. and 1.4 million of that is going to be an idle cost. That's a red flag to me. I want to be able to click this and see what I can do to save some money. So what I'll do here, I'll click optimize. This is going to bring us into a cluster specific page. And now we're looking at a little bit more in-depth details on where the resources are being used, and where that money is kind of coming from. So again, cluster cost here, $2.1 million. We have the idle cost at 1.4. At the right here, we can see some of the actual utilization metrics here, and behind it, we can actually see that time series graph. So you can actually see it's going up slightly. And then on the right here, we have that memory usage. Again, just useful information to kind of see the metrics behind the cost there. Below, we have scaling events. So we have some time series metrics here on those scaling events. CPU capacity, memory information here, and then the actual event here. So now that we understand kind of, where the money might be savable, right? We can come down here and we can look at our workloads related to this specific cluster. So, picking out a random one here, we can see that autoscaling is available for this one and not actually active. Below, you can see, if it is active, it's going to show. This one is actually optimizing, so it's in the actual action of optimizing. But if we go back up to the top here, we find this auth.net deployment. And then this is going to bring us into our auto-scaling kind of ability here. So up top, we have our recommendation for scaling. So we're recommending that we set the memory on 2 containers and decrease replicas to 8. So we can see the average cost per pod currently is $3.29. After we optimize, it's going to be $4.62. And then that total impact is going to be an estimated $28, almost $29 there. So that's about roughly 43% decrease.
Hey, Kevin.
Now,
Why
yes.
is my optimized container more expensive than my current container?
That's a good question, right? And so that doesn't quite make sense, right? If you're optimizing, you would kind of expect that that this cost would kind of go down. But if you look below, you'll notice that the replicas is actually going from 20 to 8. So you're actually increasing the efficiency of cost per pod by decreasing that replica count. Nick, if you have anything to kind of further expand on that.
Yeah, but by upsizing memory on the application container, so we have an upsized memory and a downsized memory. So this pod is running 2 containers. And it looks like we're going to upsize memory on auth.net, which would be our primary application in here, which means that Datadog is likely seeing historical data that it shows that it's needs more based on what has been, allocated to it. But also in aggregate, it probably doesn't need all 20 because those are lower. So, we have our current cost is lower than the optimized cost, but the number of replicas that we'll be running is going to be less. So this kind of goes back to the idea of bin packing that we talked about at the end of my segment there. So we are still reducing cost and increasing efficiency of the application and the resources that we're applying to it.
Awesome. Thanks for expanding on that, Nick. So, we have all this information. We see that we can optimize. We make the decision to optimize. All you would need to do is you click that enable auto scaling button up there. It takes you through a few steps, and you begin that optimization straight from Datadog, right? You don't have to go into your Kubernetes environment doing things manually, getting lost like I would do. Everything can be handled inside Datadog, making it that kind of time to value is going to be, very quick. You don't have to necessarily have that super in-depth knowledge of Kubernetes. Instead, you can come to Datadog and make those changes directly from here. So I see that we have a lot of questions. That's going to wrap up my demo here. We have about 15 minutes left. So what we're going to do here is kick off a Q&A. So Jess, I will pass it on over to you.
Yeah, awesome. Thanks, Kevin. That was a great demo. We do have a bunch of questions. Let's get to that. Our first one right here. I have an application pod that has a startup issue, or startup uses almost 2 cores of CPU, when it's loading classes and such, but then hovers around 250 millicores in usage. How do I properly size my pod?
Yeah, that's a good question. A lot of times when you see applications starting, and this is like particularly true for Java and .NET type things. There's a lot of work that has to be done at startup to actually start the JVM, and it takes a fair amount of horsepower to get all those classes loaded and make sure that the application is able to run. So the tricky part here is that if we're talking about resource efficiency, yes, those are going to spike up in utilization as they start up. But then it's going to come down significantly during regular usage. So there's definitely a disparity there. And sometimes the answers to these kind of questions can be really difficult because I certainly couldn't recommend optimizing for startup time. And maybe the question winds up becoming your scaling practices and when do you actually scale? So sometimes it might take a little bit longer to start things up if you're cost conscious and resource conservative. So when this happens, if say you're only setting a limit of 1 or 1.5 and it's trying to use 2, you're going to wind up in some throttling. So your startup time is going to be longer. But maybe the resolution there is to either do some pre optimization for the container image itself, or to have your scaling be a little bit more sensitive so you are scaling up a little faster and being able to warm those up before you actually really need those pods to be active. So you have a little bit more of a window to make sure that those pods come online before you desperately need them to continue serving traffic. It's definitely kind of a hard question to answer, and there's definitely a fair middle ground between that startup time and that regular resource utilization. So this would definitely depend on some experimentation for your individual workload.
Awesome. I see another question. I can answer this pretty quickly here. So from Dan, we have a question that says, have costs for the optimization and scaling features been determined yet? And the answer to this is we don't know yet. This is going to be up to the product team. I, as a Datadog employee, don't know that yet. So, unfortunate, I don't have a specific answer for you. Down the road, once it kind of becomes GA and they figure out that cost, I'm sure it'll be public. But as of right now, we don't really know the answer to that question.
So I see another one in here that I'm going to take. What strategies have you found effective for reducing cloud spend related to resource over provisioning in Kubernetes? So I think what this question might be getting at is that sometimes a strategy is to completely over provision your cluster to begin with. And there actually is a type of container out there called an over provisioning pod, where it's meant to just sit there and be idle and do nothing and effectively keep nodes in the cluster. The reason for this is that sometimes certain node types can take a lot longer to start up. And if you're scaling because you need those, then you need them sooner than later. So having warm nodes in the cluster ready to go could be effective, especially if you have a kind of seasonal scaling pattern, like a daily sort of pattern. The trick there is that often what I notice is when the strategy is utilized, a lot of times the instance types that are used are also on-demand utilization. So thinking about cloud providers, there's a few different ways to actually schedule or purchase resources. The easiest one is when you say launch an EC2 and you just go for it, and that's on demand and the price is much higher. If you actually work with AWS and have reserved instances, the cost is significantly lower. You're effectively leasing those servers, more or less. So if you do want to over provision and have machines that are regularly in the cluster that are potentially idle, definitely consider not paying on demand cost and looking more for reserve type instances. That would be my biggest recommendation. If you do need to over provision, and that's kind of what you're getting at there, that sort of is what it is. So you do have to kind of reduce cost physically rather than doing some resource tuning, because there are certain needs for that sort of deployment. Oh, here's another one that's kind of a quick hitter that we can get to. So what are the role of limit ranges in a cluster? I've heard of them and how they can automatically set resources for you without having to do that on each deployment manually. Okay, So limit ranges are something that are super, super helpful. It effectively establishes a default of resource allocations for when pods do not specify them, or deployments or whatever resource type you're using, don't specify them themselves. However, this can also be pretty dangerous to use, because if you're running a multi-tenant cluster where you're not 100% sure about what else is operating or how they operate, and none of them have resources applied, if you apply that limit range, you are now globally enforcing those constraints against those. And it's entirely possible that instead of, having a successful attempt at being judicious in spending, you've actually affected your stability, because you've now kind of choked some of the applications that otherwise actually need those resources. So limit ranges are great if you apply them in the future, where before doing that, you make sure that everything is as well buttoned up as possible for what it needs for your critical workloads.
Cool. I got a Datadog related question here. So in order to run Datadog agent to monitor pods in a Kubernetes cluster, how do we configure and set up? Do we need to use and configure daemon set and sidecar container? If so, any handy link to go through it? So the answer to this is actually pretty simple. It's a 3-step process to install the agent, I believe. And I'll go ahead and send the link to our documentation page, but we laid out super simple. We like to offer that time to value. So installing this agent container agent pod is going to be, a 5-10 minute process. Now that gets longer as your environment gets more complex, but still that time to value there is going to be, super quick. We can get, set up within your whole environment within that, first day. So I'll go ahead, I'll find that documentation page and I'll send it in the link or in the chat.
So got a follow-up question to my comment about the reserved instances. It says, won't spot instances be even cheaper than reserved instances? Yes, you are 100% correct. Spot instances can offer really, really, really significant discounts, and sometimes upwards of 90% discounts on cloud costs. However, if we are also talking about the need for stability, the big trick and the reason that those are so cheap is that the availability of those is not guaranteed, and those instances can be interrupted when a cloud provider is under like heavy stress from other customers as well. So spots are nice because it's kind of just like leftovers that you can use. But if you're worried about stability within your cluster, using spot instances can absolutely disrupt the functionality of that cluster. So yes, they are cheaper than reserved. However, if you have reserved instances, they are guaranteed for you to be present for the term of the the commitment. Let's see, what else do we have in here? Do you think Kubernetes native tools are sufficient for cost optimization, or is an external tool like KubeCost or Datadog necessary? This is a great question. So when you're looking at Kubernetes itself and internally, and you're on the kube control CLI and everything like that, Kubernetes itself has no concept of its own cost. It could be running in Minikube. It could be running on a Raspberry Pi. It could be running on the biggest EC2 instances you can possibly get. It has no clue. It just does the work that you tell it to. So it's really difficult to equate dollars and cents directly within the cluster itself. And even so, other tools don't necessarily have that kind of ability to do that within the cluster. But something like the VPA, the vertical pod autoscaler, can actually help here. So it doesn't always just automatically resize your workloads. There is a mode that you can run it in that would report what it would scale things to based on that historical data without actually having it scale. So while that's also not going to show you dollars and cents directly, with an internal tool that pretty much comes out of the box with Kubernetes, it's one of the CNCF kind of available tools. It will help you with right-sizing workloads in your cluster, which, if done correctly, kind of inherently helps with the cost. But like I said, otherwise, Kubernetes itself is just not cost aware, since it's agnostic to where it's running, and it doesn't care what kind of instances it's on or whether or not they're on demand or that sort of thing. So there are some other tools. If you want to get down to dollars and cents, you do need a piece of software that does actually understand instance types and idle costs and everything, but you can get pretty close with understanding resource tuning with just the VPA. Let's see, I got a few more minutes here, and oh, here's a fun one. Have you encountered performance issues that were resolved not by scaling, but by tuning JVM or language-specific memory settings? And how do you account for that in resource requests? This is a great question. And I've mentioned Java a few times. Java's a great language. It does have its kind of quirks, especially when you get into performance tuning, because you wind up tapping into the dark art and black magic that is the JVM itself. And just like Kubernetes resource requests, there is no one size fits all for JVM settings. It's fully dependent on your workload, what it's doing, how much traffic there is, and that sort of thing. And JVM tuning winds up being like a little bit different in Kubernetes than it would be on like a virtual machine. So in my experience, a pretty good place to start is you basically so you're going to set the minimum heap value and the maximum heap value to be the same thing, as this allows the JVM heap to be static and doesn't require additional resource requests or expansion of the heap within the JVM, which can impact performance. So as the heap grows and grows, it resizes, it does kind of pause operations for a second. So setting those statically does allow the heap to just start at the size that it's going to be at. And then as far as requests and limits go, basically you should set the heap size to be like 75% or so of whatever the request value is, which is going to allow for that heap to be present and also allowing for off-heap memory usage. And then limits should be set to the same requests to make sure that we are in the guaranteed resource class, so we have the stability of those resources against those allocations there. Cool. I think that's about all we've got here.
Yeah, that's
Kevin,
great,
if you wanna-
Nick. Thank you. Okay, so what's next? Guys, Dash is coming up June 10th and 11th. So if you guys are going to be there, please come swing by the NoBS booth and say hello. We've got some really awesome handmade swag, handmade wooden bottle openers made by the NoBS team in our own shop. Very cool. We're also pre-booking meetings. So if you're going to be at Dash and want to lock in a time slot to meet with us, you can book that, pick a time with the QR code on the left-hand side. If you don't want to wait, or if you can't make it to Dash for some reason, then you can book a 30-minute consultation with us anytime that works for you. And that's the QR code on the right-hand side. That's a wrap, guys. Thank you so much for joining our session today, and hope everybody has a really great rest of the day.
Thanks, everyone.
Thanks, everyone. Cheers.